Thank you very much. I would like to, my talk is about one of the simple model of population dynamics on multidimensional lattice with non-random but non-homogeneous birth and death mechanism. My talk is closely related with previous talks, Елена Борисовна and Екатерина Владимировна, but there is some distinguishes. In terminology of population dynamics, we consider branching random walk with the following rules. First of all particles evolve independent on each other, and this evolution includes symmetric irreducible random walk with generator kappa L, where A, function A, is probability kernel. It is symmetric and span coordinate Z, where A larger 0 is equal to O lattice. Then particles can duplicating. It means that each particle at the site X during the small time interval can be split into two particles, into two offsprings, with probability which is proportional function B. B is the rate of splitting. Certainly, it may be considered more general laws of splitting, but for simplicity, we consider only duplicating. And particles can annihilate during small interval with the probability which is proportional to function mu. Mu is the death rate. Let designates total number of particles at coordinate y at time t, which is generated by a single particle at coordinate x at time t. And we consider the total number of particles at set gamma. Let us designate function U. It is a generating function for subpopulation which is generated by a single particle at x. And for back, we consider the backward Kolmogorov equation for this generating function. It is one type of, it is discrete type Kolmogorov-Petrovsky-Piskunov equation. If we differentiate this equation, we consider we have the equation for the first moment. I want to emphasize that the first moment equation defines by operator H, which is our Hamiltonian, which consider which is the sum of two terms. The first term is our generator random walk, and the second term is our potential. It is the difference between birth rate and death rate. If we differentiate generating function once more, we have equations for higher factorial moments, and we can see that these equations depend on the same Hamiltonian H. In my talk, there is a specific specific definition of functions B and functions mu, birth and death rates. We consider some finite set Q. It is our happy island where particles evolve in supercritical regime. It means that the rate of birth larger than the rate of death. But outside this set Q, particles can only death with constant mortality rate. We are interested in the case when parameters of considered model provide exponential growth of particle field in any side of our multidimensional lattice with positive probability. And we talk about a concept of ecological front, or in terminology of previous talk, it is propagation front. And we see that inside this front, particle field is not intermittent. And we talk about limit theorem for normalized subpopulation size. Some about the mathematical description of previous slides about happy island. We consider Schrödinger type operator when with non-homogeneous potential V. This potential depends on some finite set Q, and inside this set Q, the probability, the birth rate is equal to constant B, and outside this set Q, the birth rate is equal to 0. And death rate, mortality rate can be positive in all sides of our lattice, but it may be different inside this happy island and outside this happy island. But we consider that parameter mu is larger than 0, but parameter mu circle is less than parameter B. It means that in this happy island, we have a supercritical regime. We consider, we can explicitly express our potential in the following way. I only emphasize that our potential is not finitely supported because we have parameter mu outside the happy island. Particles can D outside this happy island. Certainly, the long time behavior of our random walk, branching random walk, depends on the spectrum of our Hamiltonian. Our Hamiltonian can be represents in sum of two terms. First of all, the spectrum of first is absolutely continuous part. The spectrum of first is the absolutely continuous part, and due to second term, which is finally supported, we have a discrete part of spectrum. We have a finite number of eigenvalues. We are interested in the case of supercritical regime in all lattice. It means that we want to know where when there is some positive principal eigenvalue. This principal eigenvalue and corresponding eigenfunction related with function green function with the following explicit formula. Green function can be, as we see in previous talks, that green function have some different representation. First of all, it is Laplace transform of transient probability of our homogeneous symmetric random walk, and it can be considered as the resultant of our operator kappa L, which is generator of our random walk. In these slides, I have extra facts about green function, but I think that I can omit these slides because it is not very important if we are interested in the proving. I only emphasize that regardless of properties of random walk, transient or recurrent, the green function is finite because parameter mu is larger than 0. That is why we have lambda plus mu is always larger than 0 for all positive for all non-negative values of lambda. I want to remind the relation between positive eigenvalue between principal eigenvalue and its corresponding eigenfunction. And if we want to consider this relation only for coordinates inside happy island, we see that it is simple equation for eigenvalue of positive symmetric matrix with the values of green function. This matrix is positive, symmetric, and positive defined, and 1 divided by big lambda is maximal eigenvalue, and function psi is our corresponding eigenvector, which is positive from Perron-Frobenius theorem. For finding when this condition is true, let us define function R, function AR, which is the maximal eigenvalue of our symmetric positive and positive defined matrix with the values defined by green functions. these functions are strictly monotone decreases from the value when lambda is equal to 0, and when we have this inequality, then we have a unique solution of our equation, and elsewhere there is no solutions. Then for sufficiently large value of big lambda, we can satisfy inequality numbered 1, or we can satisfy this inequality, but by sufficiently large set Q, because if we consider that our set Q is equal to all letters, then we have this inequality, and if we can consider the finite set Q, we can have the unique solution of our equation. And this provides a supercritical regime of considered model. Now I consider, now I want to talk about some facts about asymptotic behavior of ground state function. Because we consider the finite set Q, the large behavior of ground state depends on the value of green function. This ground state decreases as x is model x tends to infinity, but we consider two different cases. First of all, these decreases exponentially fast when we consider that our random walk have a light tail. It means that our random walk don't have far jumping, and function psi decreases slowly as power law in the case of far jumping, when our random walk have heavy tails. It is very known that in supercritical regime, the first moment of our subpopulation size has the following asymptotic. Thus, for every fixed site y, the first moment exponentially increases in time, but for fixed time t, it decreases in space. That is result in the concept of ecological front, or as Ekaterina Vladimirovna called this propagation front. The region, there are many different definitions of this front. One of the mathematical definition of this ecological front is the following. It is the region in our multidimensional lattice that separated the large and the small value of first moment of subpopulation. and we consider this mathematical definition of our ecological front. From the previous slide, we consider we see that the speed of propagation of this front is different when we consider light tail random walk or heavy tail. In the first case, the speed is linear, and in the second case, the speed is exponential. If we consider some special case when the happy island is equal to only 1 point, for example, 0, then we have explicit formula for all previous results. First of all, we can find the value of, we can find the ground state function. Then if we consider that our lattice is one dimension and we have simple random walk where particles symmetrically jump to the neighborhood, then we can represent green function with the following formula, and we can see that in this case the speed of propagation front is linear, because ground state is logarithm of ground state function is linear from function y. The second, the following slide is closely related with previous results too. We see that normalized subpopulation sites converges in L2 to limiting random value of Xi, and limit particle field Xi uniquely defined by its factorial moments. In the next slide, I want to represent some formulas which explicitly not explicitly, but can a bit of explicitly relate recursively related. M is our factorial moments, and these factorial moments recursively defined by the following equations. Function phi, it is Laplace transform of the first moment of our subpopulation size, and this Laplace transform also satisfy the following equations. When we have the special case Q, the set Q is equal to 1 point, then we have explicit formula for all these equations, and in this slide you can see this explicit formula. This result in the case of mu is equal to 0, but with general mechanism of splitting contains in the paper Bogachev and Yarovaya. From this result, we can see that inside this propagation front there is no intermittent. We see that Lyapunov exponent divided by L does not depend on L, and it means that inside this propagation front we have homogeneous particle field. I want to emphasize that for Kolmogorov-Petrovsky-Piskunov model, where we have homogeneous mechanism of branching random walk in supercritical case, we have the concept of ecological front, but inside this front, particle field is not homogeneous. The particle field is intermittent. It means that particles exhibit intermittent behavior in large part of region behind the front. Particles are concentrated only in very sparse spots there. I write a reference for this result about intermittent structure inside this ecological front. In this slide, I want to represent some formulas for generation function for limiting random walk.
Elena, sorry, 3 minutes left.
Okay, I think it's okay. Probability, and I want to say about probability generation. We can consider forward Kolmogorov equation for probability of generating, and we do a Fourier transform, and that is why we see that in the supercritical regime there is non-trivial solution of previous equation. And certainly in the simple case, when Q is equal to 0, we have explicit formula for probability of generating and probability of not generating. References for my talk. Thank you very much.
Thank you. Thank you.
Thank you very much.
Вот там на последнем слайде, было какое-то уравнение, не на предпоследнем, уравнение было дифференциальное. Вот, там было Q умножить на Q. Q на Q минус 1.
Да, но не линейное уравнение. Оно не
как же,
линейное.
какой же там это самое преобразование Фурье может помочь, если он нелинейное уравнение? А по времени преобразование Фурье, что
по времени, да.
А по времени,
простите, да. Я, простите, сама не поняла вас. Да, конечно,
по времени. Понятно, спасибо.
Да. Это дифференциальное уравнение, это обратное уравнение Колмогорова здесь записано. Так же, как я делаю с производящей функцией. Вот.
Елена, вам удобнее ответ на русском, на английском? Давайте на
Если
русском
можно на
спрошу.
русском, да, просто.
Да, основная теорема, где вы рассматриваете вот перед этим основная теорема о поведении численности частиц, до этого.
Вы имеете L2 сходимость или что?
Да, вот допустим, эта теорема. Откуда берется, как вы доказываете сходимость в пространстве L2, когда все время говорите про моменты?
Я смотрю на второй момент.
Вы здесь предполагаете существование только второго момента?
Не, ну, смотрите, когда я говорю про предельное поле, я рассматриваю все моменты. Вот это следующее утверждение как раз-таки касается всех моментов, что оно полностью определяется моментами за счет выполнения условий Карлемана. То есть я тут рассматриваю
Так,
все
но
моменты.
если у нас условие Карлемана выполняется, то мы получаем только слабую сходимость. Откуда берется пространство L2?
Ну, я рассматриваю, что это последовательность Каши в L2 смысле. То есть я доказываю, что, ну, собственно говоря, вот эта последовательность по Т является...
Елена, пришлите мне, пожалуйста, давайте так будет проще, вашу какую-нибудь публикацию, как вы это доказываете, если можно.
Хорошо. Она
Спасибо.
публикации пока нету.
Ну,
Я
не
просто
публикацию, значит,
Да,
черновики.
да.
Все, спасибо.
Хорошо. Так же, на самом деле, как у Станислава Алексеевича в работе с Караумом. То есть у них то же самое делается, только у них пространственно-непрерывная модель. То есть у них Y в RD. А там точно такая же прям теорема Карауф-Молчанов в точности.
Согласна. Только я не знаю, как вы это здесь связали с моментами. Здесь возможно действительно доказать, вот мы сделаем через Мартингала действительно существование первых двух моментов.
Не, ну вот Станислав Алексеевич ведь, ну как?
Спасибо, Елена.